Good afternoon and good evening to all of you. A very warm welcome to all who have joined today. I, Arvind Shukla, on behalf of Paleo ECR India Event Coordination Team, I welcome you all for this Paleo ECR India Community Saturday Talk Series. And as we know that this talk series has been initiated to create a collaborative platform for early career researchers and senior scientists so that we can share the ideas, research, and experiences across the broad fields of value sciences and earth system science. So actually, this is I think the first talk in the new year 2026. So a happy new year to all, and I wish you a very prosperous and a very good new year for all of the ECR community. So before I start introducing the speaker, there are a few announcements that I request everyone to keep your microphone muted during the talk. And if you have any queries, just use the chat box. We'll have a talk of around 30 to 40 minutes. And after that, there will be a dedicated 15 minutes Q&A session at the end of the presentation. So please write your questions or raise your hand in the chat while the Q&A session, and we will reach to you one by one. So now it's my pleasure to introduce our speaker for today's talk, Dr. Partha Sarathi Jena, and he's my very good colleague and friend. So Dr. Partha is basically a paleoclimatologist and currently a postdoctoral researcher at Shantou University, China. And he completed his PhD in geology from Physical Research Laboratory, Ahmedabad in 2022, and followed by a postdoctoral researcher at PRL till 2023. And now, and after that, he was also a postdoctoral fellow at University of São Paulo, Brazil from 2023 to 2025. And he completed his master's from IIT Bhubaneswar and bachelor's from Provincial University, Cuttack, and both in geology. So if you talk about his research expertise, his research specializes in the paleoclimatology and paleoceanography, and with a very strong focus on the cosmogenic nuclides like beryllium-10 and carbon-14. And he's a very good expert in handling the AMS, the Accelerator Mass Spectrometry facility. I think he ran this instrument in PRL for more than 5 and 6 years. His regional research interests include Indian Himalayas, the Northern Indian Ocean, and the Equatorial Atlantic Ocean. So with the aim of understanding the past climate variability and the ocean atmosphere interaction on centennial to millennial time scale. So on behalf of Paleo ECR India community, I sincerely thanks Dr. Partha for accepting our invitation and for sharing his time and expertise with Paleo ECR India community today. So with this, I invite Dr. Partha to begin his talk. Thank you all once again for joining us today. Please enjoy. So I'll just stop sharing. And Partha, you can share the slides.
Let me quickly share it. Can you see it in full screen or?
Yes, we can.
Okay. Right. I'll just. Is it okay now?
Yes, perfect.
Okay, so I'm very happy to be here. And first of all, before I start, I'd like to say thanks to Arvind and to all the Paleo ECR committee members. And again, also a great thanks to everyone who has joined here to listen to my talk, which could be pretty boring. I don't know about it. So Arvind actually gave a good introduction about me. I'm very flattered about that. So I will also go on and quickly introduce myself because the primary aim behind building this community was to we get to know each other either in the present or in the future. Whenever we get a chance, we try to talk to each other and collaborate. So my name is Partha. I am currently working as a postdoctoral researcher in the Shantou University in China. But before going before coming here, I started my research journey in IIT Bhubaneswar as a master student. There I worked on foraminifera. Then I moved to PRL and also in collaboration with IIT Gandhinagar. There I worked on cosmogenic nuclides. Then I did a very brief postdoctoral position in PRL again. Sometimes I forget about it. And in that, I worked on yeah, estimation of denudation rate in Himalaya. And after that, I moved to Brazil. I worked there for 2.5 years on uh, uh, on ocean circulation. And then just recently, 2 months back, I came to China, and now I am working on evolution of Chinese deltas. So I have worked on a very variety of geological fields. So this is kind of my expertise on which I have worked on, starting from Himalayas to Atlantic Ocean to Chinese deltas. I have worked on lots of geochemistry, starting from geochronology, including cosmogenic nuclides, to isotope geochemistry. So in the figure, you can see this is me. This is a picture from Ladakh, where I am sitting on a Rosi Mutni, which is a typically glacially eroded landform. This picture is from Leh, and this is on a paleo lake. And this picture is from PRL, where during my first year of PhD, and this is the first time I did titration, and I never did that in my 12th class. So this is the first time I also learned what titration actually is. And after that, I went on to doing column chemistry. And this is the instrument that I worked in PRL for 5 years almost. So with this brief introduction, I will go start talking about the about the subject. So the title of today's presentation is Centennial Scale Intensification of the Atlantic Meridional Overturning Circulation during Heinrich Stadial 1. It's difficult. I mean, it's even difficult for me that I don't remember. I'm looking at it and reading. But what you can see here is that there are specific terms, for example, Atlantic meridional overturning circulation. So you can guess that I'll be talking something about the ocean circulation. And again, during Heinrich Stadial 1, that means I'll be focusing on a specific period. And centennial scale. Centennial scale means I'll be talking about time period of 100 years. And in terms of sediment cores, marine sediment cores, we can say that this is a pretty high resolution record. Okay, and this is the work that I did when I was in Brazil, and this work has been done in collaboration with multiple people. You can see them, and most of them are people who work with proxies, but there are a few people who work with modeling also. For example, Martin and Gerrit, they are modelers. So this has been a collaboration between people who work with proxies, who do lab measurements, and the people who sit in front of computers and do difficult modeling simulations. And this work was funded by FAPESP. So I'll start. So this is the first introductory slide. So maybe many of you already know what it is, and people who already work with paleoclimate, nearly know it. So I'll briefly explain it. So we have something called thermohaline circulation. It kind of involves that there is a water mass movement throughout the globe, and it involves surface water as well as deep water. and at some specific regions the deep water forms and it comes out at a different place. But what it does, that because it travels throughout the globe, whatever the climatic perturbation we observe at a specific place, it transfers it, and it also transfers particularly heat along with it. So it kind of balances the heat that we observe in earth today. And along with that, what it does, that because it goes, the surface water goes in at some specific points and it doesn't get into contact with the atmosphere for long. So once it goes in, it takes lots of CO2 along with it until it comes up again. So CO2 is stored inside the water, and because of that, it also affects the atmospheric CO2. Okay, so it can affect a lots of climatic processes, but I highlighted heat as well as atmospheric CO2 because I will be talking on that. Okay, now if I focus on the Atlantic Ocean part, and in the talk I will be focusing on that, we call it the Atlantic Meridional Overturning Circulation. And this is because first it happens in Atlantic, meridional because the water mass movement is along, it's nearly along the longitude. So that is why I call it meridional. Overturning because at some point the water mass goes in and again comes out. So that is why the term is overturning term comes. So in this talk, I'll be focusing only on the Atlantic Ocean part. So what happens here is the water mass, the surface water goes in here in the North Atlantic, then it travels as cold water, and again it comes with the atmosphere only in the Southern Ocean. So it kind of balances the heat as well as CO2 in this region. Okay. So first, I will talk about the heat distribution. If you can see this schematic, what it shows that you imagine this is the North Atlantic and this is the Equatorial Atlantic. So if the AMOC is stronger, what it does, it transfers the all of the heated water from here to the North Atlantic. So it gets balanced. But when AMOC is weaker, a lots of heated water gets accumulated here because it is inefficient in transferring that water to the North Atlantic. So because of that, because lots of heat gets accumulated here, now the ITCZ that kind of defines where the wind will meet and precipitation will occur, that is kind of dependent on where we have the maximum heat. And now because we have the maximum heat towards the south of equator, we get a lots of precipitation in the country of Brazil in the northeastern South America. So now the hypothesis is that the ocean circulation can affect the precipitation over land. Now, have people seen it? So there has been a study by Mulija et al. Stephen is actually a co-author in this paper. What they did is they took one sediment core from here. This is South America, and you can see this place is Brazil. And what they did is they measured the protactinium by thorium ratio here, which is a proxy of AMOC, and they measured delta D, which is a proxy of precipitation. Along with that, they measured iron by calcium and sedimentation rate, which are also related to precipitation. Now, what they observed is whenever AMOC is weaker, for example, during HS1, we see increase in precipitation rate. So now what we hypothesized in the previous slide, people have already seen it. In terms of millennial scale resolution, they have already seen it. Now, what happens? Now that was precipitation. Let's talk about CO2 a bit. Okay, now imagine this is the North Atlantic Ocean. This is the Southern Ocean. Now, once this water goes in, it takes lots of CO2 along with it. Now, AMOC defines how fast this water will reach Southern Ocean. If AMOC is slow, that means this water will stay inside the ocean for a long time. That means now this CO2 is cut off from the atmosphere. But if it is very fast, now that CO2 gets transferred to the Southern Ocean very quickly. Now that CO2 gets a chance to come up again, but it cannot come up very quickly because there is another process, that is the upwelling in Southern Ocean, that controls if the water mass here will reach the surface or not. If upwelling is stronger, that means the water mass can come up. If upwelling is weaker, that means the water mass, even if AMOC is stronger, the water mass cannot come up. And once it reaches here, there are other processes such as degassing processes that can affect if this CO2 will get released to the atmosphere. So it is a very complex phenomenon. I mean, lots of processes affect how the CO2 will get released from ocean to atmosphere. But the thing is, here, let's assume that these processes are insignificant, though they are not. For simplicity, we will consider only flushing by AMOC as well as upwelling. Now, there was one study by Anderson et al. 2009, which was a significant contribution to the understanding of atmospheric CO2. What they did is they took a sediment core from the Southern Ocean. They measured the opal flux. Opal flux is a proxy for upwelling. Now, what they observed is that whenever you see high opal flux, that means increased upwelling, that at that time you see the increase in atmospheric CO2. Now, opal flux is low, you see the atmospheric CO2 kinds of become stagnant. Now, once again high opal flux, it starts increasing. So what they said is that though AMOC is an important phenomenon in terms of regulating atmospheric CO2, it plays a passive role. Its impact is not seen directly on the atmosphere. Rather, the upwelling in Southern Ocean is the more dominant factor that controls the atmospheric CO2. Now, till that time, it looked like everything was solved. Now, we had a very clear understanding what affects the atmospheric CO2 and what doesn't. But then what happened? There was a group led by this guy Marcotte. What they did is they measured atmospheric CO2 at a very high resolution. You can see here these blue points at a very high resolution. Now, what did they find out? That this period is HS1, that not only atmospheric CO2 rises, they found some events when atmospheric CO2 rises very rapidly. I mean, it rises about 20 ppm in 100 of years. And within the last deglaciation, they found three such events, 1, 2, and 3, when the atmospheric CO2 rises very rapidly. Now, there was another study after this group measured the atmospheric CO2. The study was by Chen et al. 2015. What they saw is that during this sudden increase in atmospheric CO2, we see sudden strengthening of AMOC. For example, you see this blue bar and this blue bar. At that time, we see sudden strengthening of AMOC. So that means that though in millennial scale timescales, uh, the upwelling was the most dominant factor, if you look at these sudden CO2 rises, AMOC played a significant role in terms of supplying lots of CO2 to the Southern Ocean. Okay, so it is a critical interplay between AMOC strengthening and upwelling. But what interesting was there, for this particular event, they didn't find any significant AMOC strengthening. Maybe because of the resolution of the proxy and limitation of some proxies. So the main motivation behind this study is that we had to find that what exactly happened during this event. So now you imagine how the motivation of this study has been defined. So the millennial scale events have been clearly understood. So the motivation behind our study is to understand what happened during this event, very small but significant event. So for that, we use a proxy, that is the radiocarbon ventilation age. So you see how this proxy works. Maybe most of you know it, but for some people who don't know, that potency is produced only in the atmosphere, and so for to the ocean, the only source is atmosphere. Okay. Now here, once the deep water goes in, it takes the CO2 as well as 14C from here. But once this water mass goes in, the 14C source is cut off. Now 14C will start to decay. Now, what happens? If the water mass movement is fast, that means 14C will decay less. We will have more 14C. Now, if it is slow, that means 14C will decay more. We will have less 14C. Now, if we measure 14C in the bottom water, we can talk about how fast this water came from here to reach here, how fast it arrived at the study location. But what to do in the past? If we want to study in the past, you take benthic foraminifera and measure the 14C concentration in benthic foraminifera. But to that, we take plantic foraminifera as a reference, so that such that we get a reference to understand how fast this water mass has moved. Okay. So, but in this study, what we did, we took a sediment core, we measured foraminifera, we separated foraminifera and measured 14C in that. But along with that, we did some model simulation. In the model simulation, we took a R system model. We put some parameters. These parameters are specifically what they talk about, how the climate has changed in the past. And then we put the atmospheric radiocarbon, and then we did the ventilation as simulation. So now we have numbers from measurements as well as number from simulations. Okay. Now, now I will. This is the sediment core. Though in the map it looks very close. It has been collected from a water depth of 1400 meters nearly. Now, what you see in this figure is that you see this color is more towards yellow. That means 14C is less depleted, and here the 14C is more depleted. And this is the 14C at 1400-meter depth. That means this water has more 14C. That means the water mass movement is from north to south. Okay, so as we expected, that water mass goes in the north and then goes towards south. And there has been one study that by Leopold et al. 2016. They did the neodymium isotope study in this region, and they say that the neodymium isotope doesn't vary that much. That means the source has always stayed the North Atlantic. Source has always stayed that the water mass comes from the North Atlantic. Okay. Now, but the thing is that uh, because our proxy is radiocarbon, we cannot directly go and build chronology on radiocarbon dates, because it always assumes a constant reservoir age. But in the past, the reservoir age has changed. So what we did is that we did some stratigraphic peak matching, and from stratigraphic peak matching, we found the calendar ages. Then we tried to see how the past reservoir age had changed in the past. So this is the gray points are the reservoir age that we calculated in our study. And the green one is the model results from our study. And the other colorful ones, they are from some published results. So what do you see that they almost agree with each other? So finally, we build a very high resolution record based on radiocarbon, but with varying past reservoir age as well as stratigraphic ages. So now we have a good control on our chronology. Now with that, this is the numbers we have. We have almost 45 planktic and 45 benthic radiocarbon ages. So we have 45 ventilation age numbers in our study. So, but before I interpret B minus P ventilation age as a proxy of AMOC, I had we had to do some testing, because all the proxies we have, which we talk that they are actually proxies of AMOC, they have their own limitations. So does radiocarbon ventilation age. Sometimes other parameters, they do affect it. So we had to do some testing. So what we did is that, now if you look at this figure, the first one, so here we have the blue one is B minus P ventilation age from our reconstruction. This is the B minus P ventilation age from modeling. And this is the AMOC strength from modeling. So what do we see is, on millennial time scales, they agree. For example, if we see HS1, when the B minus P ventilation age is higher, the AMOC strength is low. AMOC is on a opposite scale here. So again, if we come to let Bolling Alaroid, we see that B minus P ventilation is low, such that AMOC strength is high. So they are oppositely related, but we see some kind of relation. But then what we did is that we put all the data points in a plot, but then as expected, we see a opposite correlation. You see the red line. But when we look at them very carefully, what do we observe? That this positive correlation is actually defined by a few data points, only these ones. But these data points, there is no correlation. So here we cannot say that there is a good correlation. So what we can say is that there is a correlation when the AMOC strength is less than 10. That means in our study, B minus P can be treated as a proxy of AMOC only when the AMOC strength is weak. But if the AMOC is stronger, it doesn't behave as a good proxy for the B minus P ventilation age doesn't behave as a good proxy for AMOC. So with that, we only assume that here we can treat B minus P ventilation age as a good proxy for AMOC when AMOC strength has been weak, and HS1 has been one such period when AMOC strength has been already weak. So to use this proxy, HS1 would be the most suitable period. So here we only use this as a proxy for HS1. Now what we find out that, you see, this is our B minus P ventilation age. This is the gray one is the whole HS1. We find out that during early HS1, we observe high ventilation ages, but during late HS1, the ventilation age is high, but we see some variability. The first one is during almost 16.3 kiloyears, we see a sudden strengthening of AMOC in terms of low ventilation age values, and one at 15.4 kiloyears. Now, if you look at this black one, this talks about the precipitation in northeastern Brazil, and the precipitation record also responds very quickly. Now you see almost the precipitation was high. You see the arrow that if you go down, precipitation increases. So it was almost high, but at these points and these points, precipitation reduces. That means it also, it kind of responds very quickly, that almost during HS1, the ITCG was southward, but at these points, the ITCG moves north, so we get less precipitation in Brazil. Now, if we look at the atmospheric CO2 curve here, the last one, the green one, at this point, we also see an increase in atmospheric CO2. So what do we say is that this event at 16.3 kiloyear, which maybe has a similar kind of source behind the atmospheric CO2, that the strengthening of AMOC supplied lots of CO2 to the Southern Ocean, and which got released because, again, upwelling plays a role because upwelling was going on, but the source of CO2 suddenly comes from due to strengthening of AMOC. And at this point, we also see a slight increase in atmospheric CO2, nearly 5 ppm compared to 20 ppm here. So we say that this event was much smaller, but this was a pretty significant event. So based on that, this is our conclusion that whatever changes we see in terms of AMOC and circulation, so the climatic impacts are very rapid. I mean, within a few years, it can affect the precipitation in Brazil as well as the atmospheric CO2. But the thing is, I will end with some future perspective. Though we said that atmosphere, we talked a lot about atmospheric CO2, but this is not, this is not that this is we solved everything. So first of all, to understand how much CO2 was actually supplied by AMOC, first we need to have some modeling that we didn't do in the study. And again, because the study is from 1400-meter depth and no other study has seen it, so we cannot just say that this 1400-meter depth the AMOC was strengthened. So first we need to have studies from deeper depths to understand if the whole water column was strengthened. But but there is a tricky part, because once you go deep, the sedimentation rate decreases, so finding a high resolution record is tricky. So maybe somehow we have to do that in the future. And but the another thing is, though it said that the AMOC was strengthened, if there was CO2 stored in the ocean or not, to check that, we have to have some pH related proxies to check that there was CO2 stored in the ocean which was supplied. And apart from that, the most interesting question that this study raised is that, within 100 years, we see these peaks. So that implies that the whole Atlantic Ocean was, the water mass movement was suddenly rising, then stops within hundreds of years. So what exactly caused that event? So we do not have an answer to that. So maybe some studies at the source region could be able to attend to that. Then fifth, if uh, there was some kind of strengthening with that, and I said that it affects the North and South Atlantic heat balance. That means when there is strengthening, that means it would have affected the temperature in the Southern Ocean. So that means we can, if we can build a high resolution temperature record, then we can at least check if that affected the Southern Ocean temperature or not. So with that, I will end my talk. These are some pictures from my happy times in Brazil. And thank you again, everyone, for attending. And you can ask me some questions, or you can contact me. I am available. I mean, all the social media platforms, I am available in all. Okay, thank you again.
So thanks, Partha, for this wonderful talk. And now the floor is open for the Q&A session. If someone has any doubt, any question, any suggestion, please do raise your hand or write in the chat box, and we'll reach out to you. Actually, we encourage ECRs to come up and ask the question, do the discussion. That's the main important, section of this talk. So, yeah, the floor is yours. Anyone? Shanton Day. Yeah, please go ahead.
Thank you, Vaya. This is a very nice talk. Am I audible?
Yeah.
Yeah. I just have one question, like regarding the protactinium thorium for as a ventilation proxy and 14 carbon ventilation edge. So, like according to you, which proxy is like most robust for AMOC strengthening and ventilation?
Okay. To answer that in my way, to for a better AMOC proxy, I would say protactinium by thorium. Why is that? Because that is a proxy for how fast the water mass moves. But in terms of, I mean, ventilation is, there are lots of processes that can affect. I mean, I can list a few. For example, I mean, the surface reservoir is how well it interacts
Yes,
with the
yes.
atmosphere, and how it and if there is some mixing or not. If the water mass residence time is higher and the organic matter they fall and they get oxidized, that also can
Mhm.
affect 14C. 14C is actually not a proxy of AMOC. Rather, it is a proxy of how isolated deep water is from the 14C source. So there is a
Okay.
kind of tricky difference between them. So it is not I mean, AMOC is the dominant factor that affects it, but it is a proxy for how isolated deep water mass is from the 14C source.
Yes, actually, when protactinium thorium is limited, when the particulate flux is much higher, so we cannot use that very reliably in that this kind of settings. So in that case, 14 carbon gives us a very good results.
Yeah, yeah,
That is
maybe. So that is why everyone says that it's better to have multi-proxy. And till date, protactinium by thorium has been, treated as the benchmark that how we understand AMOC changes. But in our case, also you can see the protactinium thorium has not responded to these centennial scale changes, while B
yes,
minus
yes, yes.
B responds. So there are some limitations, but overall, I would say protactinium thorium would be a better proxy.
And I just have another question. For AMOC strengthening of greater than 10, you just mentioned that radiocarbon 14 carbon is not very good suitable,
Mhm,
not very well correlated.
mhm.
So regarding that, I just want to know why when the AMOC is strengthened, why it is like that.
Okay, so this is a very good question, and we have been, the reviewers in our paper have asked the exact same question. So this is there is a tricky answer to that. That the plot you see here on the right, this is a I would say this plot is only valid in our location. So if
Okay.
you go to another location, the plot maybe would be different. And why is that? Now you see, our location is very close to the North Atlantic.
Mhm.
Now when water mass movement is very quick, at present we get similar to 300 years of ventilation age. Now, when the water mass movement is very quick, the error in that it's not error is that is so high that we may not be able to distinguish between when it was first and little first and first, if it was there are small differences between that. Now, if I
Okay. Okay.
come to Southern Ocean, maybe I would expect a better straight line.
Okay.
Okay, so
Okay.
it is not universal. This is very this is a plot only for our study location.
So it is like the uncertainties associated with AMOC strengthening and the ventilations.
Yeah, because at that point you see these are two the numbers we are getting are 200. Okay, I have not
Mm-hmm.
shown the errors because these are modeling results and they do not usually produce errors, but expect that the errors will be very higher. Okay, now in 800 you get 100 years of error, and you get 200 you get 100 years of error. Now here
Okay.
actually all values are same. You see, though they are different, actually they are all same. You know,
Mm.
so that
Yes.
is why when it's actually slow, now we get to see the difference between them. Now, if that is faster, we do not see any difference.
Mm. I understand. Thank you. Thank you, Bhaiya. Thank you very much.
Thank you for the question.
Yes. So we have Salman. Salman, please go ahead.
Hello, hello,
Hi,
Partha ji.
Salman.
Thank you so much for a excellent talk. It was really informative. Thank you so much. Actually, my question, I think Sayantan already has asked. My question was same like he asked the second questions, but
Okay,
still
okay, okay.
something I can add to into this. Like you mentioned the when the AMOC is strong, we lose the C14 signal. So, but when we have like two intervals, like where the AMOC is strong, where another interval where the AMOC is weak.
Mhm, mhm.
So when you compare between both of them, how you tackle that?
Okay. I forget if I have some spare slides or not. Yeah. So it is actually, in that way, it is clearly distinguishable in terms of that. Uh, you know, it, when we compare between, now I will come to that slide and explain to you here. Now, you see, if we take this as one data point, let's say this is the Bolling aneroid, then we can clearly distinguish between what happened during HS1 and Bolling aneroid. But if I talk about what happened within that Bolling aneroid, then it fails. But it's not like we cannot use that between as a proxy between HS1 and Bolling aneroid. Okay, but the issue is
Okay.
here. I mean, we cannot say this one is actually different from this point. So the issue is here. Now I will again come back to this slide. Now you can see, we see clear differences between HS1, Holocene, this is Younger Dryas, this is LGM, and this is Bolling aneroid. So within that we see clear differences.
Okay. Thank you so much.
So
Yeah, should I move back or yeah? Otherwise there should be
okay,
question on
so
that slide.
no, I think Dr. Ramanan has raised the question. Please
Yes.
go ahead.
Dr. Partha, can you hear me?
Yeah, I can hear you. Hello. Thank.
Hello.
Yes,
Actually,
I
I'm
can hear.
traveling. If my voice is getting break, please let me know. Yeah, actually, I have one small observation in the your slide because your core depth is uh, thing is that so far we have this atmospheric CO2 get trapped in the deep sea, part of the reservoir part and heat part also. And for your slide, I am just able to see that whether this intermediate water masses, can they also trap a lot of heat and CO2? That was not estimated so far, I think, from global oceans. If you're seeing some papers from Pacific, by Rosenthal and all, otherwise no papers, I think.
Yes.
Are you
So
getting my point?
yeah, I got it. I got it, and that is a very good question. So this is where the limitations of this study lies, and to answer that, if I say that this study solved all the CO2 question, that this is not, because at 1400-meter water depth we have very less CO2, and I agree in that term with that, because all the CO2 was mostly stored in the deep waters. And because this depth was affected by NADW, and NADW not only affects this depth, it affects from 1000-meter to almost 3000 meters. So we expect that because this we see at 1400 meters, the same should be seen at 2500-meter depth, or let's say 3000-meter depth. We expect that. And
Partha,
but yeah, please.
Partha, I'm making it is little simple. Like
Okay.
this southern ocean, we have this AI, the Antarctic intermediate water mass. Whether this
Mhm.
Antarctic intermediate water masses bringing some heat from to trap those heat in the at intermediate depth in the tropical regions, say for Atlantic, Pacific, and the Indian sides, and along with the CO2 also, because recently I've seen two to three papers from Pacific by Ojanta. It is actually they estimated some of the MGYC, and to estimate at intermediate depth what are the temperature causes at glacier interglacier cycle. Not very recent time. So, so far the studies that we are seeing so far, it is the only the deep water estimation in terms of coming for the CO2 and regulation part of the at different time scales. But I think intermediate water masses in terms of the heat and CO2 is not studies. That's what my observation from your slide.
Yes, I got it, and you know, I don't have an exact answer to that. One thing I know that AIW can hold lots of CO2 compared to NADW because it comes from Southern Ocean, and there is already lots of CO2 available. But here, we are trying to check if there is some role of NADW, and I am not exactly sure how much CO2 was stored in the intermediate depths. That we have to see with some pH related
Okay,
properties.
fine.
Okay,
Yeah,
so
this is just observation from a slide.
yeah, I got it, and thank you for pointing that out and giving me some inputs. So yeah,
Yeah.
yeah, I don't. Sorry, because I don't have exact answer to that, but we can discuss it.
It's okay. It's a nice talk anyway. It's nice talk. Nice to
Thank you for
listen.
that.
Thank you.
Okay, Partha, so we have one or two questions in the chat box. If you can read, or should I read it for you?
Okay, let me check.
Yeah, so Niharika asked.
Consider for the modeling of ventilation is I want to ask the factors are considered for. Okay. So this is regarding the modeling, and I have I don't have a very in-depth knowledge about that. But what I know is that because I'm not a very expert in modeling, so what we do is the present model is in our case is ClimberX model. So I am giving you specific terms that if you work with modeling, you will know better than me. So this is the ClimberX model that talks about the present scenario, and then we give it the past factors. For example, first Milankovitch cycles, then the gases, and most importantly we give the the past ice changes. That is a very new model, and the name of that is paleo mist, and we give this past changes, and after that we put the radiocarbon in it. In terms of radiocarbon, we give the how the past changes in radiocarbon has happened in terms of int cal. And but I can say what we have not considered in our model, because we here we have not considered any biological processes that could have also affected the 14C. That is one of the shortcomings of our model. But maybe with this answer I only know that much. I don't know much deeper into it. So maybe you can find some answers from from these terms.
Okay, so Dr. Pradyuman, please go ahead.
Hi, Partha. Very nice
Hello,
and well structured talk, Partha. Should I?
hello, yeah, thank you.
Hello. I have
Yeah,
just
please.
posted message in the chat box. Should I read, or are you okay with it?
Okay.
If you can ask it, it will be better. We can interact.
Okay, Partha. I have just a small query regarding sedimentary hiatus. What specific features in AMS radiocarbon age depth relationship indicates the presence of a hiatus in sediment score? Just a small query. Sometimes I'm little bit confused with it.
Okay, sedimentary hiatus has specific features in. Is it about okay? Sedimentary hiatus is. Okay, let me think about it. It's not related to my presentation, right? If I'm
Yes,
getting
yes,
something.
yes, yes. Yes, yes. That's why I have asked you.
Okay,
It's
okay.
just a small query. Okay,
Yeah.
you are basically from geochronology, so I have asked this question.
Yeah, you this is a kind of difficult to know. I mean, from directly from AMS ages,
Okay.
unless you have a very high resolution record, if there is any hiatus.
Hmm.
And because nowadays I am working with delta, we see a lots of hiatuses. Even that is
Means this how we can identify the sedimentary gap between the through linear sedimentation or something else. I just want to know that. Because most of the time I'm confused with it.
You get a lots of dates, and you see, if you see any gap, then it would be hiatus. I don't know what is the exact thing.
Okay. I will discuss you with it later. Okay.
Yeah, maybe I will discuss with it later. And
Okay.
are you seeing any hiatus in marine course? I mean,
yes, I will
in
show you
marine
my.
course?
Okay. Yes, I will show you. Okay, later. Okay. Thank you, Partha.
Yeah, okay, yeah, then there is a tricky part, because in marine sediment course we just take the S depth model as a continuous one.
So anyone else? I think I don't see any question in the chat box. So okay, I have some queries and some kind of inputs in the talk. So regarding the Dr. Ramanan's discussion that you were talking about the CO2, I think what, if I understand correctly, like the CO2, the role of AIW in supplying CO2. So one thing is that first of all, the formation of AIW in the Southern Ocean is is in like more warmer condition, okay, rather than the Antarctic bottom water. So it's around 2.7 degrees centigrade, and Antarctic bottom water forms around 1.9 degrees centigrade. So the warmer water masses, like they store less CO2. So if you compare in between the AABW and AI Antarctic intermediate water, yes, you can say that the bottom water is more good in storing the CO2, and it can supply the more CO2 in the equatorial oceans compared to Antarctic intermediate water. But then relatively, if you talk about the Antarctic in between CO2 and oxygen, then Antarctic intermediate water is like more rich in nutrient and oxygen compared to the CO2. So yes, you do kind of like get the signature of this, but it's not that easy, because you don't know like which water mass is from southern and which one is coming and ventilating a particular type, because the bottom water became the intermediate in the like Southeastern Arabian Sea. So it's very tough to identify like whether it is Antarctic intermediate or just like the bottom water is becoming deep and intermediate. So it's very tricky part, but yes, it can supply some kind of CO2 in the atmosphere.
Yes.
If we can measure it properly. And
Thanks
the
for
second
the
thing is like
clarification.
yeah. And second thing, like whenever we talk, like in your talk, you're discussing about the use of this proxy, the ventilation age, and in compared to like rotating thorium for HS1. So okay, let's move a little bit more from the HS1 to HS2. Does this proxy will work for HS2? Why I'm asking, because we usually in the paleoclimate we consider most of the HS events like a cold and dry HS events. So usually we have a very common practice to say like okay, this is significantly high or low in HS periods. So does it only restrict to the HS1, or will it work for HS2 and other like HS events?
I think it should work for HS2. Why I am because in my next project we are supposed to try that, but I just left the position. But if we go to HS3 and more, that would be tricky, because now we are getting reaching towards the saturation point of radiocarbon.
Yes.
And we get very less radiocarbon, so the errors will be much higher. So I'm not very sure with such high errors we'll be able to separate between these small scale changes. So because I think for radiocarbon HS1 would be the best one now, because we get lots of 14C counts in AMS and the error is less. So maybe that is the point. I right now I am unable to think any other processes that could affect. But in terms of the limitations of radiocarbon, I can say that this could be the answer.
Yeah. So like now we are like pretty much sure about these things, that all the cold distance does not behave same for this like limitation of the region, the proxy, the archive, the tool. So we have to be very careful when we are talking about all the cold events are showing something. So that is like quite significant from all this listening now. So if anyone has a question, please come ahead and ask. And if not, then just let me check chat box finally. Okay, so we have almost, I think you answered all the questions asked from the people. Okay, so if not, then I think I'll wrap up this session. And thanks to Partha for accepting our invitation and giving us such a nice, wonderful, I think, a very nice talk. And thanks everyone for joining. And we'll see you soon. Next, I think maybe the first week of February with some more interesting talk. And the next talk will be more on the sulfur isotope regarding the Himalayan weathering. So like we are going from the quaternary to 10 million time scale. Okay, so thank you so much, everyone. Thank you so much.